Welcome to tutorial 6.1 part 1. This is on the wave nature of light, and all we're going to do is look at a simple property of light, the relationship between the wavelength and the frequency. We're going to need this information to build up some ideas about how electrons exist in a hydrogen atom, and for us to understand those ideas we have to be at least remember some of these relationships about light. So let's have a look at it. So first of all, the speed of light is going to be designated with the letter c. Light can vary by its size or wavelength, but all types of light have one thing in common. As you know, they all travel at a set speed, the speed of light. And we have to be clear what that means in a second, but first let's just get used to the number. We can designate it in miles per hour or miles per second, kilometers per second, but we're always going to use meters per second. So this number here you should kind of commit to memory, 3 times 10 to the 8th meters per second. And it's important to note that the speed of light is the same regardless of the frequency of light. And some students get a little bit confused about the difference in speed and frequency, and we'll try to make that nice and clear here. Long wavelength radiation has lower frequency, and short wavelength radiation has higher frequency, but importantly all radiation travels at the same speed, at least in a vacuum, the speed of light. Alright, so let's have a look at it. Getting used to the symbols. First of all, the symbol for wavelength is lambda. It's just the Greek letter. It's like their lowercase l. And different types of radiation have different types of wavelength. So as you know, radio waves, for example, are different than ultraviolet rays or infrared rays. So what are we distinguishing when we distinguish their wavelength? We're distinguishing this property that I try to draw some arrows here so you knew what I meant by the wavelength. I think you probably know. It's the distance from either the peak to the peak of a wave or any two corresponding parts of a wave. So this is kind of like the middle part of it. It's kind of coming down here. On the other wave it's the same, or the trough at the bottom. So it's just the distance between those two, and it kind of marks the distance between these periodic disturbances that create the wave in the first place. Alright, this distance is known as the wavelength. It's often abbreviated with the Greek letter lambda, or that kind of funny looking symbol there. And it can have any unit. We're often going to use the units either meter or nanometer. Not too often that we're going to worry about centimeters, but we will sometimes use nanometer. You'll see why, because it's kind of the atomic scale, or meters. All right, so let's look at another property. The other property is the frequency of light. It has this letter nu. It's also a Greek letter. And what it means is how many peaks of a particular wave pass by some location in a unit of time. So if you were kind of sitting there watching these waves come by, and you would count them 1, 2, 3, that's how many passed in a unit of time, like a second, you'd say that would be what the frequency is. We're going to measure it in hertz. The abbreviation is HZ, meaning how many waves went past per second, or how many peaks per second, or cycles per second. And we'll write it both ways, like this, HZ, or sometimes though just mathematically it's going to seem clear if we write 1/second, meaning how many waves have passed in a second. So the unit is just the inverse of a second. You might not like that -1 there. It just means 1/second. And we'll abbreviate it as the letter nu and write it like this kind of V, like with a little tilt to the side. So let's look at an example here to make sure we're clear about both wavelength and what we mean by the frequency as compared to the speed. So here's like this little diagram of a wave. And the question, first of all, is this wave as you see it, what's the wavelength? You say, well, let me see, from crest to crest, it looks like these lines here show me that they're like a ruler. The distance is 3 times 10 to the 8th meters. So it looks like the wavelength is 3 times 10 to the 8th. What if I change the wave? I made it a different wave, so I'm going to drag this thing in a little bit. Well, now what's the wavelength? I see, well, I can tell what happened there. The distance now from here, from crest to crest, is no longer 3 times 10 to the 8th, but 1.5 times 10 to the 8th. So that's easy enough. Now let's try another one. Let's change the wave again. What's this wavelength? Well, here it doesn't quite line up with this line, but I can tell there's 1, 2, 3 waves that cover the distance from the left here, from 0 over to 3 times 10 to the 8th. So it must be 3 divided by 3, or 1 times 10 to the 8th. Must be the wavelength between those waves. And we could keep going like this. I don't think there's any need to, but let's just do one more. What would be this wave over here? I can see there's 1, 2 that fit between 0 and 1.5. So it looks like 0.75 times 10 to the 8th is the wavelength for this wave. Alright, so now let's look to see what we mean by the speed of the wave. So I'm going to go back to the original one and say, what do we mean? We say that a wave of light travels at 3 times 10 to the 8th meters per second. Well, what we mean is that this crest, or any corresponding part of the wave, is going to take 1 second to get from here over to there. So watch me move it and pretend right now this is going to take a second. I'm going to say ready, set, go, wave. And right now it's moving, it's moving, it's moving, moving. And when it gets to there, 1 second has passed. So it's a little jerky on the mouse. Let me try it again. So we're going to say, all right, let's see how fast this wave goes. Wave goes. It's going to take 1 second to get from here to there. So we say ready, set, go. And I'm keeping track of time. It's not a second yet. It's not a second yet. It's not a second yet. Oh, now 1 second has passed because now that crest has made it over to 3 times 10 to the 8th. How does that change when I change the wavelength? So let's go to a different wavelength. Now you can see the wave is half as long as it was before, but it's still going to be the same thing in terms of the speed. It will still take 1 second for this wave to get from here over to there. So let's move and try it again. So ready, set, go. It isn't there yet. It's not there yet. It's not there yet. It's not there. It's halfway. It's halfway. And now, 1 second has passed. So you should be able to tell that this speed was the same as the last one, but of course the number of waves that passed at a certain point will now have doubled. I have 2 waves that passed, and we can kind of see that if we look back. By the time 1 second has passed, this wave and this one will get to that same point. So we'll have a frequency of 2. 2 waves will have passed, but the speed will still be 3 times 10 to the 8th meters per second. Let's just do one more. Let's change the wavelength again. Same thing. The distance, this crest has to take 1 second to get from here to there to have a speed of 3 times 10 to the 8th meters per second. But of course you can see 3 waves will pass in that same amount of time. So the frequency of this wave would be 3 because 3 waves will pass by a given point in a second. We'll watch it go. Ready, set, go. It's going, it's going. Hasn't gone, hasn't gotten there yet, hasn't gotten there yet, hasn't gotten there yet. And now 1 second has passed. So it went 3 times 10 to the 8th meters in a second, and in that time, 3 of the little waves have passed that particular point. Okay, I hope the point is clear enough. How do we say that mathematically? We say that the wave and the frequency are inversely proportional. The longer this wave is, the lower the frequency is going to be. But as I make it shorter, of course, I'm going to have more waves that pass in a given point, and the 2 numbers are inversely proportional to each other. So mathematically, let's see if we can see a couple of questions or just look at one question. Look at this one here. It's like the ones on the quiz. If the length of the gray arrow, and the reason I have these gray arrows is because in the exercises I kind of give you a little box to show you the length of this arrow as a reference. If the length of that arrow is 6.25 times 10 to the minus 7th, what's the frequency of that blue, the shorter wave? So you look at that, you say, let me see. Now from here to here, they tell me that length. How many waves fit in here? 1, 2, 3, 4, 5 of those waves. So it must be this number divided by 5 is the wavelength of the particular wave. So I divide 6 1/4 by 5 and I get 1 1/4. So let's look at that first. So I divide by 5. Okay, I got the wavelength, 1.25 times 10 to the minus 7th. And now I think I say, yeah, but whatever this wave is, the shorter it is, the more frequent, the more frequent it's going to go past. So I have to take this number, multiply by the frequency to get that same speed, that speed of light. So mathematically, we write it out like this. The speed's always the same when you multiply the wavelength times the frequency. You always get that 3 times 10 to the 8th number. But I want to know the frequency, so I have to divide the speed of light by lambda, by the wavelength. Here's the speed of light we've committed hopefully to memory. And we divide by the wavelength we just found. When you divide by the 3 by 1.25 times 10 to the minus 7th, you get this pretty large number, 2.4 times 10 to the 15th. And the units, if you can see here, the meters are going to cancel. You're just left with second to the minus 1. That's the same unit as hertz. So if you want to try to visualize this, this means that a particular kind of light, the kind of light that had this wavelength that we gave, 1.25 times 10 to the minus 7th, would actually pass by a given point, really an ungodly number of times. 2.4 times 10 to the 15th times is how many times those peaks would pass by in a given second. Okay, that's all there is to the quiz. It's pretty trivial in terms of the math. All you're doing is always doing the same thing. You're given a number, you divide the speed of light to get the other number. But the logic behind it, exactly what does a wavelength and a frequency for a wave mean, might take a more, a longer moment for you to think about. Great, good luck with that, and we will see you in class.